Still dealing with roots as far as polynomial equations are concerned, we now move on to rational root theorem. In the last one, we considered Vieta's formulas, which gives us a way of knowing the sum and product of the roots of any polynomial, you know, and that simply tells us that even without knowing the roots, we can know their sum and their product. And there's a lot of things we can actually do with that. We can formulate the roots. We can formulate the quadratic equation by just knowing, the sum and product of their roots. Okay, so now let's go on to rational root theorem. So in this set of notes, we'll study statements of the rational root theorem and its interpretation, how to generate candidate rational roots, how to test candidates using substitution or synthetic division. We assume all polynomials have higher integer coefficients like that. Okay, so let's go ahead. General formula of a polynomial. I mean, we've seen that several times. So consider a polynomial with integer coefficients. P of x equals a sub n x raised to power n plus a sub n minus 1 x raised to power n minus 1, and so on and so forth up to the constant a naught. That's you can also go in terms of, say, ax squared, whatever. If you are dealing with a quartic expression, for instance, that'll be a x raised to power 4 plus bx raised to power 3 plus cx raised to power 2 plus dx raised to power plus dx, right? Plus e. All right. But what if you have a polynomial that has like more than 26 terms? So this is a more general way of writing that. So where all coefficients ak, all the an minus 1 up to a1 and a naught are integers. So we're assuming they are integers, and an is not equal to 0. Of course, if an is 0, it reduces the degree of the polynomial by 1. So that's why that has to be guaranteed. So an is said to be the leading coefficient, and a naught is the constant term. And from the very beginning, this leading coefficient and the constant term have been very useful in everything we've been doing. So let's talk about the statement of the rational root theorem. So the rational root theorem states as follows. Suppose P of x is a polynomial with integer coefficients. This expression, same one like before. If P of x has a rational root of the form x equals P over Q, where the great common divisor of P of and Q is 1, that is nothing, you can't divide them further. That's what that simply means, because nothing is common to them. That is, they are in their simplest, they have been simplified. And Q is not 0. I mean, if Q is 0, this will be undefined. Then this P now, the numerator, is a factor of the constant term, a naught, okay? And Q is a denominator. Q, the denominator, is a factor of the leading coefficient, an. That is this an now. So in essence, we are saying that for x equals P over Q, we are saying that P is something like a factor, something. P is actually a naught divided by something, and Q is an divided by something. And that is why, to get the roots of a polynomial, that's why we always like to divide by a. We always have to do a naught over an. That will give us a clue as to what the possible roots of the expression of the polynomial can be. So equivalently, we can simply say that every rational root of the polynomial P of x must be of the form P over Q, basically, where P divides a naught and Q divides an, with GCD of P of Q equals 1. So in essence, what we are simply saying is we put a naught over an and simplify, that you get the equivalence of PQ. That's basically the idea. So it means we are looking for the root of a polynomial. You just so one clue you can have is from a naught over an simplified to the made in the simplest form. So let's look at a special case when we have monic polynomials. Now, so a polynomial is monic, like we know, if the leading coefficient is 1, right? So, here we had an x raised to power n. What if that an is equal to 1? That's what a monic polynomial is about. So instead of an xn, you just have xn, because the coefficient of xn is 1, and so on. So in this case, any rational root PQ must satisfy this, that Q divides 1, Q divides 1, which implies that Q is equal to plus or minus 1, right? Because normally what we should be having is P over Q, so P over 1. So Q must divide 1, So q is either plus or minus 1. So any rational root must be an integer dividing the constant term a naught. That has to be something dividing the constant term a naught. So rational roots are a subset of integer factors of a naught. That's what we are saying. So once you have a naught, so whatever the integer factors are, those are the possible roots you can have for the polynomial. You'll get to understand by the time we take examples. In fact, I've done such examples in the past. This is just like adding giving it some mathematical rigor, mathematical structure to all I've been doing. So talking about the interpretation and intuition, the theorem does not guarantee that a polynomial has a rational root. Now, there was this, I think video 10, on the 10th video, the last question I did, you can see I tried all the possibilities for a particular polynomial, and I did not get any rational any rational roots. Maybe I didn't try hard enough though, but this is so it's not every polynomial has a root. That's simply what we're talking about. So the theorem does not guarantee that a polynomial has a rational root. It says that if a rational root does exist, it must appear in a finite list of candidates. So this is useful because it reduces infinitely many rational numbers to a finite set of possible rational roots. So intuitive idea, very brief, is that if P of P over Q is 0, that is, if you evaluate the polynomial by, if you evaluate the polynomial using P over Q and you get 0, and the highest common factor or GCF, greatest common factor of P and Q is 1, and an integer coefficient. Then after clearing denominators, divisibility arguments show that P must divide the constant term A naught, then Q must divide the leading coefficient AN. This divisibility structure is the heart of the theorem, basically. So just look for the leading coefficient and look for the constant, that's all. So, and put the constant over the leading coefficient, and then you can see the possible results you can get. So let's look at how to generating candidate rational roots, the general procedure. Okay, I think I want to expand this and just keep going step by step. Okay, look at this now. So how do you generate candidate rational roots? I mean, this I have done a couple of times. All those times that we have a random polynomial and we keep trying, try x equals 1 to see if you evaluate the polynomial by at 1, it gives you 0. This kind of things. That's you trying to look for candidates of solutions of roots to the polynomial. So given p of x equals an normal with integer coefficients, we generate candidate rational roots as follows. Step 1, factors of the constant term a naught. Okay, so pick a naught. So it pick any possible factors of a naught and begin to try. So like yesterday, I had, yesterday in the 10th video, when I was working at it, you discover that the constant was 24. So I started with plus or minus 1. I went to plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, because it's 24, plus or minus 8. If I went as far as plus or minus 12 and I didn't get anything. So my guess is possibly that polynomial does not have a solution. I mean, it does not have factors. It's not factorizable. Possibly, or maybe I didn't get something right. Those are the two possibilities. So factors of the constant term a naught, right? List all integer factors of a naught, both positive and negative. These are the possible numerators of P, right? Then step 2, factors of the leading coefficient an. List all the integer factors of an, both positive and negative. These are the possible denominators Q, right? So then you can now, from step 3 now, you can form all fractions P and Q, all the possible fractions from all numbers of the form P over Q, where P is a factor of a naught and Q is a factor of an, So include both positive and negative possibilities. So simplify each fraction to lowest terms and remove duplicates. So the resulting simplified fractions are the candidate rational roots. So it means that you can get all the possible rational roots of a polynomial by just following this procedure. So okay, now we have come to that point where we practicalize what we've talked about. So imagine you want to generate candidates. What are the possible rational roots for this cubic expression, 6x cubed minus 7x squared plus 2x minus 1? So the first thing, the constant term is minus 1. Okay, so what are the factors of minus 1? Plus or minus 1 are the factors. So plus 1 minus 1. The leading coefficient is 6. What are the factors of 6? It can be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So you can then form all possible fractions P over Q So in that case now, with P being plus or minus 1 and Q being plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, then the possible formulations you can have are, so it means you're going to have plus or minus 1 over each of these. So plus or minus 1 over plus or minus 1, you have plus or minus 1. Plus or minus 1 over plus or minus 2, that's plus or minus 1 over 2. Plus or minus 1 over plus or minus 3, that is plus or minus 1 over 3. Plus or minus 1 over plus or minus 3, that's plus or minus 1 over 6. So the candidate rational roots of this polynomial are this. So if you want to try which of them are factors, you can start with plus or minus 1. So don't go further. Don't try any other thing. So you cannot then try all these other fractions. Okay. I don't know if I should try to do that. Maybe that's not necessary. But with this now, if you want to, so this gives you clear picture of the possibilities you should try as far as this equation is concerned. So it's like, so whatever you have here over whatever you have in the leading coefficient. So for monic polynomial, things are a bit easier. You don't have fractions. So for monic polynomial like this, let P of x be x raised to the power 4 minus 3x plus 2x minus 6. The leading coefficient is 1, so it's monic. So you don't have to worry. If you divide by 1, you always get whatever. So you can concentrate on the constant. So therefore, any rational root must be an integer in that case. So the constant term A0 is minus 6. So the factors are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. That was what I was doing yesterday with that 24, but I did not factor in the idea of having 3 in front of it, right? So in that case, I should have jumped straight to 24 over 3, 8. So I should have tried minus 8 and plus 8. So knowing this will save you stress. You don't have to try. There are some candidates you should never try because they are not part of the rational roots. So the only candidate rational roots here will be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So, and then you can then afterwards, you can then talk about testing candidate substitution. Okay. So once we have the list of candidates, we test each candidate R. So method, you can do direct substitution. So for each candidate R, you can compute P of R. If P of R is 0, then R is a root, also called the 0 of P of X. That is the idea of factor theorem, which I did. I think that must be I'm not sure what video that is now. Okay, it's one of the earlier videos. So if P of R is not 0, then you can discard that candidate and move on. So this method is straightforward, but can be time consuming for many candidates or high degree polynomials. But it's a very elite way of factorizing polynomials or solving them, getting their roots. Okay. So you can then test candidates using synthetic division. We've done synthetic division a couple of times for sure. So this is another overview of that. So synthetic division is a quick method for dividing a polynomial by a linear factor x minus r and checking whether r is a root. Suppose P of x is the same polynomial type we've been looking at general. So to test r, write the coefficients in order. So an minus 1, a1, a0. If any power of x is missing, insert a 0 for its coefficient because that's useful. As you're going to see, by the time I'm rounding off, I'm going to try a problem, and you see all these things I've been talking about. Then you need to write r to the left of the row of coefficients, then perform the synthetic division steps. So you bring down the first coefficient unchanged, multiply r by the number just written at the bottom, write the result under the next coefficient, add down the column, repeat until you reach the end. Now this may look abstract, but don't worry, I'm going to work at it. So the final number is the remainder now. So if the remainder is 0, then x minus r is a factor and r is a root. Then the other numbers are the coefficients of the quotient polynomial of degree n minus 1. So that will give you whatever is left after you've factorized out x minus r. So a very good example of synthetic division is what we have here. Let me see from practice questions. Do we have, okay, I mean, it's still a long way off. Should I come for this later? Maybe I should come for this later. So I'm just going to go through all the things we come across. So I'll just go through them. And then when I come to the end, I will now take a question and solve it clearly from the beginning. So using synthetic division, so we can let P of x, so let P of x equals 2x cubed minus 3x minus 6x plus 12, generate possible candidates. So for A0 is 12. The factors are plus or minus 1, 2, 3, up to 12. Therefore, A3, we have 2, that's plus or minus 1, plus or minus 2. So candidates before simplification, the possible candidates are plenty. So from 12, right? So you have 1 over 1, you have this, 1 over 2, you have that. Okay, you have 1 over 1, you have 1 over 2 right there. Then next you have 2 over 1, that's 2 here. 2 over 2, that's still 1. Nice. Then you have 3 over 1 right here. Then 3 over 2. This is it right here. Then 4 over 1. You have 4. 4 over 2. You have still 2 here. You have 6 over 1. That's it right here. You have 6 over 2. Coincides with this 3. Then you have 12 over 1. That's it right here. And you have 12 over 2, which is 2 plus or minus 6. So those are the possible candidates. So then you can then, after simplifying duplicate, this list remains essentially the same. So you can see, for instance, 3 over 1 and 4 over 3 over 1 give us 3. Okay, there 3 over 1 give us 3, 6 over 2 give us 3. We don't write it twice. Just don't bother. Once it's there already, you don't write it down again. So that's talking about after simplifying duplicate. This list remains essentially the same. So don't forget, get the constant, get the leading coefficient, and then get their possible factors. So step 2 now, you now test x equals to using synthetic division. For instance, you have plus or minus 1. For me, I can start from plus or minus 1. I'll try that. If it gives me 0, I'll go. So that's what I'm going to do when we get to the end, when we get to the practice question. Okay, so after simplifying duplicate, this list remains essentially the same. So test x equals to using synthetic division. To do synthetic division now, you have the coefficients of the polynomial are 2 minus 3 minus 8, 12. Okay, so you have 2 minus 3 minus 8, 12. So synthetic division with r equals to, okay, maybe I get to do this synthetic division to just clarify. Okay, so 2 minus 3 minus 8, 12, right? And then we are trying with r equals to. R equals to is our C now, or yeah, that's our R. 2 minus 3 minus 8, 12. This is where I come to. So for synthetic division, 2 minus 3 minus 8, 12. So I like to fence this off. Then I have something like this. And then since our R is 2, so these are the coefficients. All these are the coefficients of the original polynomial. This is the R we are trying out, meaning that, so if that works, if you get 0 here at the end of the day, it means that x minus 2 is a factor of the polynomial 2x cubed minus 3x squared minus 8x plus 12. That's basically what that implies. And what this is saying is, bring down these 2 now, bring it down, okay? 2 times 2, 4, put the 4 here. Minus 3 plus 4, that's 1, okay? Then 2 times 1, 2 times this 1 now, you have 2. Minus 8 plus 2, that's minus 6. And 2 times minus 6, that's minus 12. Minus 12 times minus 12 minus 2. 12 minus 12, 0. Okay, so that's 0. So that means that, so you can say that x minus 2 is a factor. Mind you, this is r, right? So x minus r is a factor. Okay, this is r right here. So x minus r is a factor. And the remaining polynomial, can I say the remaining, is it the remaining? Let me say the quotient, and the quotient is given by what you have here. Okay, so that's like minus 6x raised to power 0, 1x, 2x squared. So that will be 2x squared plus x minus 6. That's what is remaining. So this is quadratic now. You can easily factorize. So when I get to the end, I'll take an original problem and deal with it properly. So you see now we have 2x squared plus 8x. 2x squared plus x minus 6. That's what exactly we got right there. Okay. So 2x squared plus x minus 6. That's what our synthetic division gives us. So synthetic division is so cool. The only thing is that it only works for linear factors like x minus 2 that we have there. So see, all the stories I have there is what I just represented in that table, which is easier to follow in the table like that. So if you master that table thing, you don't have to, it's very easy to go to work around. And then, now that you get the quadratic, now it's easy to factorize. So you factorize, you get 2x minus 3, x plus 2. And then you have x minus 2, 2x minus 3, x plus 2. And then equal to 0, you have 2 here, 3 over 2 here when you equate to 0, and minus 2 here. So these are the rational roots now, okay? So you see, they actually match. You have 2. You have 2 there. 3 over 2, you have 3 over 2. Minus 2, you also have minus 2. So, that's plus. So you have plus or minus 2, and then 3 over 2. So you can see those 3 are the specific candidates selected from. So you can see nothing goes out of this candidate. So once you master this, it helps you to know exactly where you should be looking for your solution. So you don't go all over the place looking for it. So we have strategy for factoring with rational root theorem. When you want to factor a polynomial using the rational root theorem, ensure integer coefficients. If necessary, multiply the polynomial by a constant to clear fractions and decimals. So that really helps. And generate candidate rational roots. So use factors of a naught, that's constant term, and a and leading coefficient. Then test using simple candidates first. Try x equals plus or minus 1, like I like to do, plus or minus 2, and so on, before fractional candidates like plus or minus half, etc. Fractional candidates, of course, can be problematic. Then when you find a root, okay, when you find a root, you can factor out x minus r using synthetic or long division, then reduce to a lower degree polynomial. Then you can then repeat, apply the rational root theorem and factor further until you end with a quadratic, which you can solve with factoring or the quadratic formula, or no rational roots are found. So if you don't find rational roots, then remaining roots may be irrational or complex, and you leave it like that. So we can have special cases and common pitfalls. This is really important. So if you have zero constant term, if a naught is 0, then p of 0 is a naught, which is 0. So x equals 0 is automatically a root in that case. Then p of x now will just be x times q of x. So for some polynomial, so that is if there's no constant attached to the equation, if the constant is 0, automatically x is automatically a root, and then you have the quotient, the polynomial, which is also the dividend here, equals the divisor x multiplied by the quotient. So for some polynomial q of x, and you can apply the rational root to q of x and then continue. So be careful. So once you don't have a constant, it means 0 is a factor automatically. X equals 0 is a root, I mean. And if x equals 0 is a root, that means that 0, that means that x is a factor, yes. And that's why we have x here now. That's why x is a factor. So missing terms now. If some powers of x are missing, insert 0 coefficients when doing synthetic division. So in this case now, x raised to the power 4 minus 5x plus 1. I think I've solved a couple of problems with missing terms, and I demonstrated how you need to insert zeros to make up for them. So this has coefficient list 1, 0, 0, minus 5, 1. So here now, x raised to the power 4, coefficient 1. X raised to the power 3 is not there, so the coefficient 0. X raised to the power 2 is not there, coefficient 0. Then x raised to the power 1 is there, that's minus 5. Constant, that's 1. And that goes like that. So what if we talk about no integer coefficients, non-integer coefficients? So the theorem requires integer coefficients. So if the polynomial has fractions or decimals, of course, it's easily multiply the entire polynomial by a suitable constant to clear denominators, then apply the rational root theorem to the resulting integer coefficient polynomial. So if you have fractions in your polynomial, clear them out by multiplying through by something that will get rid of all of them. So polynomials with no rational roots. So what if there are polynomials with no rational roots? So if none of the candidates works, then the polynomial has no rational roots. So if you list all the candidates and none works, they have no rational roots. So, but we still have real or irrational or complex roots. Example, if you have q of x equals x cubed minus 3x plus 1, a naught is 1, the factors are plus or minus 1. A3 is also 1, the coefficient of x cubed. So it is monic. So the candidates are plus or minus 1. So if you check now, so the only possible candidate is either plus or minus 1. So if you put 1 here, I think that's probably what happened yesterday when I was working with that particular polynomial. So if you put 1 here, you have 1 cubed minus 3x plus 1. So that gives you minus 1, which is not 0. So that means that x minus 1 is not a factor. Then if you try minus 1, these are the other possibility. This is the other possibility. If you try minus 1, that's minus 1 plus 3 plus 1, and you get 3, which is not 0. That also means that x plus 1 is not a factor of this expression. So those are the only candidates. And if that happens, it means that q of x has no rational root. So I believe that this problem I was solving in video 10, I think, the last question I did possibly has no rational roots, because I tried the possible candidates. In fact, the only possible candidates should be plus 8 and minus 8, and I tried them and I didn't get any results. So most likely that polynomial has no rational roots. So we have some worked examples for all rational roots. Find all rational roots for p of x equals x cubed minus 4x plus x plus 6. So a naught, that's a constant, you have 6. You have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And a3, the a3, that's it's monic, so that's simply 1. So the candidate rational roots are just the factors of a naught. So this, then you can begin to test the candidates. So if you test candidates by substitution into the original expression, x cubed minus 4x plus 6. So if you try p of 1, you don't get 0. You try P of 2, you get 0. So that means that x equals 2 is a root. So you can then factor using synthetic division with r equals 2. Okay? So since x equals 2 is a root, so you can factor using r equals 2. So coefficients, don't forget, are 1 minus 4, 1, 6, 1 minus 4, 1, 6, and everything is represented. And then if you do the long division, again, so see what you get here, x squared minus 2x minus 3. So I think I'm going to do that again. 1 minus 4, 1, 6, and you're using 2 again. 1 minus 4, 1, 6. Okay? Okay. So again, we have another one. This is 1 minus 4, 1, 6. Don't worry, I always like to fence this off because I want to get the remainder here. If it is 0, that means that is the factor. So if we use 2, which we found to be to work, so all you just need to do is this one, drop it, okay? 2 times 1, 2, put that here. Minus 4 plus 2, that's minus 2. Okay, next, 2 times this 2 times minus 2, that's minus 4. Okay, 1 times minus 4, that's minus 3. I mean 1 minus 4 rather, not times. 1 minus 4. So take, you have 1 and you are owing 4. Take away the 1, you are still owing 3. So 2 times minus 3, that's minus 6. So 6 minus 6, 0. So this 0 tells us that x, that tells us that, so x minus 2 is a factor, okay? Because we got 0 here. But if we had a number here that is not 0, that means that's the remainder. So since x minus 2 is a factor, what is the, and this is now the quotient. So Q of x, the quotient is x squared, that's x raised power 0, x raised power 1. So that's x squared minus 2x minus 3. Then this is quadratic, and you can easily factorize, and you move on. So as I promised, I'm going to solve a full problem by the time this whole thing is done. So you can see x squared minus 2x minus 3, just like what I got here, x squared minus 2x minus 3. Okay, so now you can factor the quadratic, and you have x squared minus 2x minus 3. That is x minus 3 into x plus 1. And you just solve that, and you have x equals to 3 and minus 1. And those are part of the candidates, right? So the possible candidates you've got are, so this is, you have 2, 3 minus 1. So you have plus 2, plus 3, and you have minus 1 here. So because plus or minus 1. So, so your solutions don't ever go out of those candidates. So I have some practice questions here, and I think maybe I'll solve question 1 or anyone. Okay, since I've not done a quartic problem before, I think I'm going to take this quartic one. It's x raised to power 4 minus 5x squared plus 4. It's going to be lengthy, but I think it's fine. So to drive the point, I've always been solving cubic problems. So let's do quartic this time around, where we have x raised to power 4 minus 5x squared plus 4. So the question is, list the candidate rational roots and then find all rational roots and factor completely. Okay, so I'll go for that. Yeah, so you can try other ones. And if you need me to solve any other one later, I can solve it and put it on the, I have a playlist for fast math solutions where I just solve single problems here and there. Okay, so let me do, but I also feel that, okay, yeah, let me just do this and keep it moving. All right, let me just keep it moving. So yeah, so I'm solving this first question. I use the rational root theorem for each polynomial below. So P of x equals 2x cubed plus 3x minus 8x minus 3. So here now you have the possible candidates will be minus 3 over 2, right? Minus 3 over 2. So the factors plus or minus 3, this is plus or minus 2. So all that. So you have 3 over 2 and all of that going. So let me do this number, what number now? The quartic one. So let me do the quartic one. That's where did I find it? Okay, the questions are a lot. Oh, question 2 now. Question 2 is what I'm taking care of. Okay, so you have question 1 to 3 like this. This question 1 to 3. Then you have question 4 to 6. Okay, then you have 7 to 8. Or maybe we can do 1 to 4 at once. And then we can do 5 to 8 also. So these are the set of questions. So I'm taking question 2. So this one, x raised by 4 minus 5x squared plus 4. So I list all the candidates' rational roots, and I find all the rational roots and factor completely. So let's go. So I think the question is just, the overall question is to factor completely. Okay, the overall question is to factor completely. Factor completely P of x equals x raised to the power 4 minus 5x squared plus 4. Okay, so so the first thing I'll do is to find the, okay, I'll just say to find all possible rational roots, all possible rational roots. Okay, since this is quartic now, so it means that first of all we get the a naught. A naught is equal to 4 here. That's a constant. So a naught implies that we have the possible factors here, plus or minus 1, plus or minus 2, and plus or minus 4. These are the possible numbers that can divide 4. That's what that means. And then we have A4. A4 is the coefficient of x raised to the power 4. So A4 now is equal to 1, interestingly. So all we have there is plus or minus 1. Okay, so the possible rational roots are, if you divide all through, you just get 1, 2, and 4. That's all. So plus or minus 1, plus or minus 2, then plus or minus 4. So it means any solution to this, if this problem has a solution, it will not be out of this range. Okay, it's not be out of this range. So the next thing we want to do is to find. So we now want to find an actual factor. Find an actual factor, at least for starters. So don't forget we have P of x equals x raised to the power 4 minus 5x squared plus 4. So for me, I like to start from the very basic. So first of all, I try, okay, I guess I can change. So I try x equals 1. So to try x equals 1 means that I have P of 1 equals 1 raised to the power 4 minus 5 1 squared plus 4. Okay, let's see if this works. So P of 1 equals 1 raised to the power 4 is 1, 1 raised to the power 2 is 1 times 5, that's 5 plus 4. Thankfully, this is sweet. So P of 1 is equal to 0. So even from the first one we got, we are good to go. So P of 1 is equal to 0. Okay. As such, we have R to be equal to 1 is a root. R equals 1 is a root of the polynomial. It is a root of the polynomial x raised to the power 4 minus 5x squared plus 4. So it is a root of it. So, I mean, this is sweet. Yesterday I did like 7 or 8 and I didn't get anything close to 0. So, so this is really interesting. So now that we have got a root, then we can then do synthetic division. So I can just say to find the other factors, using synthetic division, So mind you here, this is an expression. It has power 4. It doesn't have power 3. It has power 2. Doesn't have power 1. It has power 0. So you have anything that is missing, you have to fill it up. So first of all, you can say P of x is the same thing as x raised to the power 4 minus 5x squared plus 4. So to fill up everything that is missing, you have x raised to the power 4 plus 0x cubed minus 5x squared plus 0x plus 4. So any degree that is missing, you have to fill it up. If not, the synthetic division will not be good. So don't forget our R is 1 already as what we found. So we now do the synthetic division proper now. So here I have this. So for the synthetic division, I have the coefficient of x squared as 1, coefficient of x cubed as 0, the coefficient of x squared as minus 5, the coefficient of x, that's 0. Then the last one, which I like to put apart, that's the constant, which is 4. 4. And don't forget, we are dividing by, we are using 1 as our division. So here we then have, so what do you do first? Bring down this 1. Just bring it down normally. So it's not this one now. So this one is on its own. So bring down this one. Then 1 times 1, 1. So 0 plus 1, that's 1 again. Okay. So now this 1 times this 1 now, that's another 1. Minus 5 plus 1, that's minus 4. Okay. 1 times minus 4, that's minus 4. 0 minus 4 is still minus 4. Then 1 times minus 4 now is minus 4. 4 minus 4, 0. Okay. So, I mean, that confirms that x minus 1 is a factor. So we say, so x minus 1 is a factor of the polynomial p of x, and the remaining quotient, the quotient, the quotient now will be a cubic factor because we are dealing with a 4-degree stuff. So, and the quotient is, so start from here. I think I want to change the color. So start from here. X raised power 0, x raised power 1, x raised power 2, x raised power 3. And the quotient is x cubed plus, okay, we can say that's q of x now. And q of x is x raised power 3, x raised power 2, minus 4x minus 4. Okay? So this one now, we have it there. So in all, so overall, we can say that p of x, which is equal to x raised to power 4 minus 5x squared plus 4, is the same thing as x minus 1, which we have got already, into x cubed plus x squared, all right, minus 4x minus 4. So now the next business is to take care of this guy, okay? How do we deal with that? So to factorize q of x, which is x cubed plus x squared, x cubed plus x squared minus 4x minus 4. So you see, this is a cubic thing. Now we can't just factorize directly. So what are we going to do again? We get the possible candidates again. So we get all possible rational roots. All possible rational roots. How do we do that? So in this case, now we're dealing with q. So let me just call it q naught. So the constant q naught is equal to minus 4. And it has all these possibilities, plus or minus 1, plus or minus 2, plus or minus 4. These are the possibilities for it. And then we get q3, q3 now, that's the coefficient of x raised to power 3. So q3 now is 1. Thankfully, that's simply plus or minus 1. So the possible rational roots are, so it should just be everything here, because each one divided by 1 remains the same. So the possible rational roots are plus or minus 1, plus or minus 2, and plus or minus 4, like this. So with that in place now, then we start the whole business again of trying which one can work in q of x. So for q of x now, which is equal to, I think it's x cubed plus x squared, if I've not made a mistake. Yeah, so minus, right? X cubed plus x squared minus 4x minus 4. So we try x equals 1, try with that and see if it works. Q of 1 is simply 1 raised to power 3 plus 1 raised to power 2 minus 4 into 1 minus 4. Okay, so Q of 1 is equal to 1 plus 1 minus 4 minus 4. Sadly, the Q of 1 is 1 plus 1, 2. 2 minus 4 is minus 2. So everything is minus 6. So minus 6 is not equal to 0. What does that tell us? We can say, so Q equals 1. Should I say that? Q equals 1 is not, I'm not using R again, okay? So Q equals 1 is not a root, of Q of x, okay? So it is not a root of q of x. So we can go ahead and try another one. So we can try x equals minus 1. So try x equals minus 1. So if you try x equals minus 1, so we have q of minus 1. Okay, q of minus 1 now is equal to minus 1 raised to power 3 plus minus 1 raised to power 2. I think that's the deal. Then minus 4 into minus 1, then minus 4. Oh, sorry, that's minus 4 into minus 1 minus 4. I think that's how it works. X cubed plus x squared minus 4x minus 4. So q of minus 1 now is equal to minus 1 raised to power 3 is minus 1. Minus 1 raised to power 2 is plus 1. Minus 4 times minus 1 is plus 4 minus 4. This is looking good. So q of minus 1 is simply 0. This cancels this, this cancels this. That is 0. That's happy. So on 2 tries, we get that. So therefore, q equals minus 1. All right. Q equals minus 1 is a factor, the factor of q of x. Okay. So now, so we proceed to do a synthetic division. We'll do a synthetic division here. Okay. So again, we go the same procedure. So don't thankfully we know the coefficients. That's everything is complete. X cubed, x squared, x. So that's 3, 2, 1, 0. Everything is complete. So the coefficients are 1, 1, minus 4, minus 4, right? So that's what we are going to need for the synthetic division. Okay. And then on the other side, we have minus 1. So we have this now. So 1, 1, minus 4, minus 4. I like to set this apart. And then I have minus 1 right here. So we know that means that x plus 1 is going to be a factor for sure. So what do you do first? Drop this 1, drop it. Then minus 1 times minus 1, that's minus 1. So 1 minus 1 is 0. Okay. So next thing, minus 1 times 0, you have 0 right here. Then minus 4 plus 0, that's minus 4. Then minus 1 times minus 4, that's plus 4. 4 minus 4 plus 4, that's 0. So of course that we can say so x plus 1. Don't forget, this is x equals minus 1 originally. So if you transfer it over, that's x plus 1 equals 0. So x plus 1 is a factor, of q of x. Okay. And the remainder and the coefficient and the quotient rather, and the quotient. So since it was q already before, we can say q of 1 of x is now, so you see this is x raised to power 0. I mean, this is x raised to power 0, x raised to power 1, x raised to power 2. So that means we have 1 times x, so that's x squared. 0 times x is not there, so x squared minus 4. Okay, and that's looking very good, by the way. That's looking very good. So we can say, so q of x, which is x cubed plus x squared minus 4x minus 4 is the same thing as that factor, that's x plus 1 into x squared minus 4. Now, don't forget where we're coming from. The original place we are coming from is this. And don't forget we are coming from p of x. And p of x, which is x raised to power 4 minus 5x squared plus 4. So don't forget, I mean, you can easily forget because it is lengthy. So the first thing we factored out was x minus 1, right? So we have this x minus 1. So don't forget x minus 1 into this now. So we now have x minus 1. So this will be x minus 1 into this q of x we had before. So x minus 1 into q of x. Okay, that means we have x minus 1 into the q of x has been factored into x plus 1 into x squared minus 4. Okay, so x minus 1, x plus 1 into x squared minus 4. Happily, this is looking great. Okay, this is looking very good. This is looking very sweet, in fact. So that is difference of 2 squares. So normally if it was something else, we would have taken it apart, but we can just do it straight. So we can say that p of x now is equal to x minus 1 into x plus 1. Then this is difference of two squares. This is like x squared minus 2 squared. So we can just do difference of two squares. We did that under special factorizations. So P of x is now x minus 1, x plus 1 into x minus 2, x plus 2. You know, that's what difference of two squares is about. That's a squared minus b squared is always a plus b into a minus b. So finally, we are factorized completely, okay? So we are factorized completely. Everything is now in linear terms. What else are we expected to do? I think we are supposed to solve, right? So once you are factorized, the solving is easy. Find all rational roots and factor completely. Okay, we have found all rational roots now. Okay, so let's just complete it. Okay, let's just complete this. So P of x equals 0 implies that we have x minus 1 equals 0, or x plus 1 equals 0, or x minus 2 equals 0, or x plus 2 equals 0. So that simply means that we have x equals 1, x equals minus 1, x equals 2, right? X equals 2, and x equals minus 2. Okay? So, I mean, the solutions now are plus or minus 1 and plus or minus 2. So, and that falls in the original rational set we started out with. You know, these are based on the original problem, these are the possible rational roots. So these two satisfy it. And that's how that goes. So it's lengthy, but I mean, once you know the process, you're good to go. So if it was like a quintic expression like power 5, so you may have to do this trial and error thing like 5 times. I mean, like one more time before you finally get. So you keep working until you get something quadratic that you can probably factorize. Okay. So this is a lengthy one, but it's fine. With this, we come to the end of this very interesting video. You want to try your hands on the rest of the questions. Try your hands on the rest of the questions. Let me know how helpful this is for you. And if there's something else you'd like me to try, feel free to let me know. If you have subscribed already, I thank you very, very, very much. If you have not subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, why not also become a member of this channel by clicking on join with some special privileges? Okay. Ultimately, don't forget to comment, like, and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing math right. Bye.